As a balloon in the shape of a sphere is being blown up, the volume increases at a rate of 4 cubic inches per second. At what rate is the radius increasing when the radius is 1 inch? So in this question, we want to use the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. The volume increases at a rate of 4 cubic inches per second. This is a rate of change. Inches per second. Cubic inches per second is the rate that the volume is changing. So we're going to represent this as a derivative. The derivative of volume with respect to time, that is the rate that the volume is changing. That is 4 inches cubed per second. You could also write this as V prime At what rate is the radius increasing? So we're looking for a rate related to the radius. So we can represent that as dr dt, the derivative. And that is our unknown in this problem. And we could also write that as r prime if you prefer. In this last part it says when the radius is 1 inch. That is a particular moment in time. As the balloon is blowing up, there will be a moment when the radius is 1 inch. And that's the moment in time that we're interested in. So we're going to use implicit differentiation on this formula for volume so that we can introduce the rates of change. Our question involves rates of change as our given information and also as what we're looking for in the problem. So we need to introduce those derivatives so that we'll have a place to substitute these values into. I'm going to calculate the derivative with respect to time on the left-hand side of the equation and the derivative with respect to time on the right-hand side. My variables don't match here, so I'll write this derivative as dv dt, or if you prefer, v prime. On the right-hand side, these variables don't match, so I'm going to have to chain when I calculate the derivative. That's 4/3 pi, that's a constant that we're carrying down, a constant multiple. We're going to calculate the derivative on r cubed to be 3r squared, but because of those variables not matching, we need to chain by multiplying by the derivative of r, dr dt. And if you prefer, you could write that as r prime. The 3's cancel, and we're left with 4 pi r squared times r prime, or dr dt. So now we have a value for v prime to substitute in, a value for r to substitute in, and our goal was to solve for r prime. So v prime was given to be 4 inches cubed per second. We got 4 pi, and r was 1 inch, and r prime is our unknown. So we've got 4 equals 4 pi r prime. Divide both sides by 4, and we've got r prime, we should be dividing by 4 pi, 1 over pi. So our rate that the radius is changing is 1 over pi. And the units, let's talk about the units. As I solve this problem, if I think about the units, let me do this in red. The units here are, which is here, inches cubed per second. The units here, for the radius, that's inches, but then we square those inches, so we have inches squared, so right here, that's inches, and when you square it, you have inches squared. We end up dividing by inches squared, and so our inches cubed cancels with the inches squared to leave 1 inches. And seconds also remain, so per second. So the units are inches per second for this problem. 1 over pi inches per second. So we have the rate that the radius is changing when the radius is 1 inch is 1 over pi inches per second. On this question, we want to find the extrema of f of x equals e to the x minus 1 on the interval from -2 to 2. So when we're looking for extrema, we're looking for the absolute max and the absolute min on this particular interval. We do have a theorem called the extreme value theorem that says as long as you have a continuous function on a closed interval, then you're guaranteed to have both an absolute min and an absolute max. This function is a continuous function, and we do have a closed interval, so we will be guaranteed to have both of these extrema. So what we want to do is find the critical numbers. So I'm going to calculate the derivative of our function, e to the x minus x. The derivative of e to the x is e to the x, and the derivative of x is 1. And we'll find the critical numbers by finding where this derivative is equal to 0 or undefined. Since this is a continuous function, it has no undefined spots. Well, not because it's continuous, because the domain is from -infinity to infinity. It doesn't have any undefined spots. I'll add 1. That's e to the x equals 1. And I can solve this equation by taking the log of both sides. When you take the log of both sides, you can use the power rule. This is the power rule for logarithms. And natural log of 1 is 0. Natural log of e is 1. So we get x equals 0 as our critical number. And we're going to use the critical number as well as the endpoints of this interval to test to see what is the maximum and the minimum. So for our x's, we're going to use both the critical numbers as well as the endpoints. However, just want to mention that the critical number must be in the interval for you to use it. So make sure your critical number is actually in the interval. And we're going to test these in the original function. We're testing them in the original function because we want to see what has the highest y value and what has the lowest y value. So we have e to the negative 2 minus negative 2. I'm going to bring up my calculator to calculate that. E to the 0 minus 0 would be 1 minus 0, and that's 1. E to the 2 minus 2. And I'll bring my calculator up for that. So in my calculator, e to the negative 2 plus 2 would give me 2.1 approximately for this first one. And then e squared minus 2 would give me about 5.4. And so we're going to choose the highest as the maximum. So the highest y value would be this one here. And I'm going to write the ordered pair in exact form. So that'd be 2 comma e squared minus 2. So I'm doing that rather than rounding. And then the lowest y value is 1. So that ordered pair for the absolute minimum would be 0, 1. Thank you for checking out my videos. Have a great day.